All right, guys, we're going to do Gauss's law for a spherical conductor. Spherical conductor of radius A. Okay. Well, if it's a conductor, let's give it a positive charge. We'll say here Q. There's a positive charge of Q. If it's a conductor, we know that positive charge of Q, well, where's it going to accumulate? In a static situation for a conductor, charges accumulate all around the outside. So that positive Q is accumulated here around the outside where the charges can get spaced farthest apart from each other. This is the least energy situation. So they're going to sit here in electrostatics. That means there are no charges no excess charges residing here inside of the sphere. So what I would want to do here with my spherical conductor, I would want to go ahead and draw a Gaussian surface. Well, again, I'm going to use symmetry here, just like I did with a point charge. I know that if this is a sphere of positive charge, the electric field is going to go off in all directions this way, like very similar to a point charge. And if the electric field is similar to a point charge going off in all directions like this, then again, I'm going to use spherical Gaussian shapes. So let me put a Gaussian shape on here. And what I'm going to do is I'm going to start with the smallest Gaussian shape possible, and that would be a sphere centered here at the same center as my conducting sphere. And I'm going to grow that Gaussian surface, increasing the radius of the Gaussian sphere until I enclose some of the charge. You'll notice that when I draw my Gaussian shape, if it's inside of the conducting sphere, okay, so here's what I want to do. I'm going to start Gauss. When my Gaussian shape is inside of the conducting sphere, okay, so right now my Gaussian shape is inside of the conducting sphere. You ask, how much charge have I enclosed? How much charge have I captured? Well, because all of the charges are residing here on the outside of the conductor, my Gaussian shape doesn't include any charges. So when I do the surface integral for the electric flux is equal to charge enclosed divided by epsilon naught, well, I get 0. I get no electric flux because the charge enclosed is 0. And then the other thing that I know about a conductor is that the electric field inside of a conductor is 0. And again, that's because we're in a static situation. If there were an electric field inside of the conductor, then the charges would be moving. They'd be moving in the direction of the electric field. But of course, we can't have an electric field in an electrostatic conductor. So there we are. We get for R less than A, the electric field is 0, and that's what we'd expect for a conducting sphere. All right, now we want to move a little bit further. Let's increase that radius of our Gaussian sphere. Okay, let's go ahead and increase that radius a little bit until, boom, right there. Now we're outside of our conducting sphere. So our Gaussian shape looks like this. It is R bigger than A. We would say now, again, all these charges are accumulating on the surface, but they have a net charge of positive Q. So when R is less than A, when I do the surface integral of E dot A is equal to Q enclosed over epsilon naught. And again, this is for the electric flux. I would say here, of course, I've enclosed all of the charge, positive Q. So my Q enclosed is positive Q over epsilon naught. And when I do the surface integral of E dot A, because I've chosen a smart choice for the Gaussian shape, the electric field lines and the area vectors are already parallel, right? Area vector, electric field lines are already parallel. So that means when I do this surface integral, the entire area of my Gaussian sphere is going to contribute. So this surface integral of E dot A just becomes E times 4 pi r squared. Remember, I'm using a lowercase r here because the size of my Gaussian shape is arbitrary. I just know that it's larger than the conducting sphere itself. Okay, so I'm still using little r because I could have drawn any Gaussian shape that is larger than the conducting sphere. So I could have drawn this Gaussian shape or this one here. I'm using lowercase r because they would all satisfy the surface integral the same way. Area of this Gaussian sphere times the electric field is going to be equal to q over epsilon naught. And then I'm going to move over the 4 pi r squared, and E is equal to positive q over 4 pi r squared epsilon. And of course, we know now that is just kq over r squared. So outside of the conducting sphere, it looks exactly like a point charge. That's what you'd expect for a point charge, kq over r squared. I don't think that's completely surprising because once you're outside of the sphere, and the further away you get from charges and geometries, we've said, eventually it's going to look like a point charge. As you get further away from things, they're going to look like a point charge, but this has the same spherical symmetry that a point charge had, so it's not surprising that the electric field is the same as a point charge, kq over r squared. Okay, so what I would do then, typically a lot of questions that they're going to ask are for you to graph the electric field. What does it look like as a function of r for this conducting sphere? Well, up until you get to the edge of the sphere, your electric field should be 0. I'm just going to darken the 0 line right there. And then once you get to once you get to the surface of the conducting sphere, then of course your electric field looks like that of a point charge. And what I'm trying to draw here is something that is proportional to 1 over r squared. Proportional to 1 over r squared, that's our electric field as a function of r for a conducting sphere. And that's it.